Okay, the second example we're going to do here in chapter 13 is going to be 13.2. And 13.2, I'm going to zoom in here a little bit. We are going to be looking at the two blocks over the pulley system that you see here. They are joined by a cable as shown. If the system is released from rest, determine the velocity of block A after it has moved 2 meters, okay? Assume that the coefficient of friction between block A and the plane is 0.25 and the pulley is weightless and frictionless. That's this right here, okay? So as you can see here, B is a 300 kilogram block, A is a 200 kilogram block. So as you can imagine, this is going to slide, B is going to go down and A is going to slide to the right. Okay. So again, we want to determine the velocity of block A after it moves 2 meters. Okay. So strategy wise, what would we use? Because now we've got options. If we go back up here, you'll notice that we fall in this area right here. We're trying to find velocities and based on a displacement of, I think did it say 2 meters if I remember correctly? Okay, the velocity after it moves 2 meters. Work energy theorem is what we're going to focus on for this problem again. So let's go underneath and get our problem set up and then work it with the equations that we have. So sample problem 13.2. Okay. Now, this one, because of the fact that B is going down, we're going to change our convention just a little bit. We're going to change the Y to go down and the X to go to the right. And this is going to be our positive convention. Okay. That way we just have fewer negatives we have to deal with later on. Okay. So, I'm going to draw our diagram first and then do givens. Okay. So our before, it's going to be on the left-hand side here, is going to be our block. Okay. And then our second state, like our after, if you would, I'm going to draw it as, and this is looking at block A first by itself without B. Okay, I'm sorry, I should have elaborated on that. So this is block A sitting where it is, and then sliding the 2 meters, in this case, to the right. Okay, so that means that this distance to this distance is going to be 2 meters. Okay, and this is going to be block A, center, center. Okay. And positive is to the right. Now, block A is going to have a weight. So this is going to be WA. We know that it is 200 kilograms mass. And there would be a normal force or a support force. And we also know that there is a friction force, right? So this is going to be friction force at A. The velocity when it starts out is 0, right? It's starting from rest. And after it's gone 2 meters, we want to find out what is that velocity. That's the problem, right? We want to know how fast that's going. We're going to call that velocity 2. And then additionally, there is a force along that cable that connects it to block B. So we're going to call this the force in the cable, and that's pulling block A to the right, okay, in the state that it's at right now. Now, as we had already discussed, because we are interested in finding a velocity and we are given distance, we are going to use the work energy theorem. So we're going to have T1 is equal to, I'm sorry, not equal to, I keep saying that. T1 plus U1 to 2 is equal to T2. So our kinetic energy in its initial state plus the work done is equal to our kinetic energy in its final state. Because we are starting from rest, T1 is going to be equal to 0. Okay, so we won't have to worry about that. We're just going to be worried about the kinetic energy after the work is done. So this will be our approach, if you would. Okay. Now, let's start with calculating the values here. Whether you start with the kinetic energy or the work is on the left-hand side. So I'm gonna calculate the work on block A first. Okay. So U1 to 2 on A is going to be equal to plus or minus force times distance. Force times distance. So the forces we have acting on this in the direction that work is done. So work is done, remember, along the same path that the distance takes. That's how I like to say it. So for instance, if this is moving to the right 2 meters, the forces that are causing or creating or engaged with that work are going to also be horizontal. Does that make sense? Our vertical forces have no effect on the work done over that 2 meters. Okay? It's kind of like, let's say I lift a package. I lift my book bag, okay, and I put it on my back. There's weight there, but that weight is vertical, okay? If I start walking, I'm not doing any work on that backpack because I am walking horizontally and the force of the weight of that backpack or me holding it up is vertical, okay? In the act of me lifting it up a distance and putting it on my back, work was done. But once I start walking, no more work is done on that backpack because the direction of the weight isn't in the same direction as the path that I'm taking, if you would. Does that, you guys kind of remember that, right? So that's why when I look at work, the vertical forces are not involved because I'm interested in a horizontal distance. So my forces have to be horizontal. Okay. So that means that I'm only going to be worried about my force along that cable and this friction force. Okay. The force along the cable and the friction force. And I'm going to use my convention up here along that horizontal or that x-axis to determine the positives and the negatives. So I can say that force times distance. Let's look at the FC first. So that's going to be FC times D. It is going to the right. So I'm going to put a positive out front. You wouldn't have to because it's a positive assumed. Okay. And then I've got a friction force going to the left. So that's going to be minus friction force times that sliding distance, right? And we know that to be 2 meters. Now, friction force, and I should put A underneath here, FFA. Friction force is going to be your coefficient of friction times your normal force, okay? So over here, my friction force at A is going to be equal to the kinetic coefficient of friction times the normal force at A. Now, the normal force at A, we don't know its value. Could we figure it out? Yeah, yeah. It's in the y direction, right? Is there any other forces in the y direction? The weight, right? Do we know the weight? We know that the mass is 200 kilograms, right? So what we need to do is, I need more room. Dang it. I'm going to leave a little gap here. If you have room to the right, go ahead. But I'm going to sum my forces in the y direction equal to 0. So I've got a negative WA and I've got a positive NA. My WA is going down, my NA is going up. It's going to be equal to 0. So I'm going to move that to the other side. As we can see, NA is equal to WA. Okay. WA, so NA is going to be equal to, we know that W is equal to mass times gravity, right? So we can take my 300 kilograms times 9.81 meters per second squared. We're in metric units. So NA should be 1962 newtons. Do you guys get the same thing? If you're doing it with me. So that's NA. Okay, so now we're going to use NA up here. So we know that our coefficient of friction is 0.25 from the problem times 1964. So our friction force at A, I got 490.5 newtons.
You were 1962 down 1964.
Oh, shoots. 62. Thank you. Thank you. 62. Yep.
Wait, 300 times 9.81, that'd be 2,943.
Yeah.
No, 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 no. Say it isn't so. Are you sure?
Hey, 300.
Oh, that's okay. Yeah, that probably is it because our mass is 200.
Oh,
I'm so sorry. I'm so sorry. It's 200 here. Yeah, I was like, wait a second. No, I know my numbers are good. I did this problem like 3 times. Okay. Now it's at 1962. Okay. So 200. Yep. 200 is our mass. Sorry, I did a 300 there. Too many numbers tonight. All right. So then now we'll take that 1962 times 0.25 and you should get your friction force to be 490.5. Is that correct? That's going to go here. Okay. We don't know what our force in the chord is, but we do know the distances too. So we can fill this in a little bit further. So we're going to have FC times 2 minus, I'm sorry, FC times 2 minus the 490.5 times 2. So our only unknown here, or the unknown on that right-hand side. So our work, 1 to 2, is going to be equal to 2FC minus 981. And that's as far as we can go with that. So we'll put that up here. So then the kinetic energy part 2 is going to be our next. So the kinetic energy block A. Okay. So this is going to be T2A is equal to 1/2 mv2 squared. So we'll have 1/2 times 200 kilograms, right? Not 300, 200 times, we don't know what V2 is. That's what we're going to be solving for. It is one of our unknowns in our problem here. So this is going to be V2 squared. So T2A is equal to 100 V2 squared. All right. And now plugging these two into our work energy theorem. So kind of bringing this down here. So this is going to be U1 to 2 is equal to T2A. This is A if you would. So we got 2 FC minus 981, which is the work side. It's going to be equal to 100 V2 squared. And that's, we'll kind of just leave that there for right now because there's 2 unknowns in that equation. We can't really go any further. Okay. So let's look at block B. Okay. Let's go to block B. You need to look at this yet? Okay, I will hold on. Where did the 981 come from? It came from 2 times 490.5. Yep, yep. There we go. All right, let's move on to block 2, or I'm sorry, block B. Okay. Now block B is the block that is hanging down. That's the 300 kilogram one. 200 was A, 300 is B. Okay. So block B. Just over here. Okay. Now this one, this is where we're going to use going down is going to be positive, just so that we don't have as many negatives. Otherwise, everything would be negative. Okay. So we're going to have block B. This is going to be, if you would, in its position 1. Okay. And then I'm going to show it down below here after it has moved 2 meters. Okay. So V1B is going to be equal to 0. That's its starting at rest. Okay. And then V2 is going to be going down here. Okay. Now, because B and A are connected by that cable, their velocity will be exactly the same. Okay. That's why we don't have a V2A and a V2B, because they're equal to each other. It's just V2 for both of them. Does that make sense? Okay. Now we know that that cable is going up now on B because it's connected up to A. And then the weight of B is going to be coming down, right? Now we can calculate that weight. So the weight of B is going to be equal to the mass of B times gravity, right? And we know that to be 300 times 9.81. So the mass of, or I'm sorry, the weight of B is going to be 2,943 newtons. Okay, so this weight is going to be 2,943 newtons going down. Okay. Now, as we look, we are going to be using, I'm going to kind of put this here. We're going to be using, as we know, the work energy theorem. So we can say T1B, kinetic energy, initial state for B, plus the work 1 to 2 of B is equal to the kinetic energy position 2 of B. Because we're starting at rest, T1B equals to 0. So we just have to calculate the work and the kinetic energy 2 for block 2. So I'm going to start with, I don't know why I did, but I started with the kinetic energy on my problem. So I'll do kinetic energy. So T1, well, no, we know T1B is already 0, so you don't have to write that again. We're going to do T2B is equal to 1/2 mv squared, and this is going to be V2 squared. 1/2 times 300 times V2 squared. So our T2B will be 150 V2 squared. That's what we'll put right there. And then our work. So our U1 to 2B will be equal to plus or minus force times distance, right? Now remember, this time we're in a vertical mode and down is going to be positive, okay? So as we look at our forces here, there's 2 forces on this block. One is due to the weight going down, and one is going to be due to our cord pulling up that is connected to A. So this is going to be equal to, because we're assigning down as positive, we're going to have a positive, I'm going to do the weight first, the 2,943 newtons times a distance of 2. You don't have to put the newtons in, remember. minus FC times 2. Okay, because FC is going up, so that's going to be minus according to our convention. So our work 1 to 2B will be 5,886 minus 2 FC. So now let's put our values into our work energy theorem. So I know that my work 1B can go here. So I'm just going to put that here. So this is going to be 5,886 minus 2 FC is equal to my T2V of 150 V2 squared. Okay. Now I'm going to call that equation number 2, if you would, or for block B. If I go back to equation number 1 from block A, I have that same form, if you would, for my work, because I've got a 2FC here, a positive 2FC, and then I've got minus 981 is equal to 100 V2 squared. So I'm going to use that same equation, but I'm going to put the negative 981 right underneath the 5,886 plus 2FC is equal to 100 V2 squared. I know. Danny's like, that is like mind blown. Yeah, Jacob too, right? So we can add these and subtract them, right? So we're going to have 4,905 plus 0 minus 2 plus 2 is equal to 350, I'm sorry, 250. 250 V2 squared. Now our only unknown here is the V2 squared, right? Or the V2. Okay. So solving for V2, this is so fun. Okay. And then it's going to be the square root of 19.62 is equal to V2. So our velocity 2 is going to be equal to 4.429 meters per second. So you kind of see what we did here for that last one. It's kind of clever. Wouldn't have done it that way. I would have probably done a 2 equations, 2 unknowns, substitution, blah, 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 blah. But this is so much easier. I'm like, oh yeah, because they're in the same form, right? Yeah. So questions? All right, so those are the 2 problems that I wanted to do for chapter 13. Let's take a peek at the homework problems that you have assigned. I'm not going to work on those tonight, okay? But I just want you to just kind of know what's ahead. And I will go back and show you guys those things. There are for module 3, there are 4 chapter 13 problems, okay? And I believe I've set you up pretty nicely for these, all right? Between the next time we're together and next week, Tuesday, all right? There'll be lots of chances to ask questions about homework and things like that. I'm going to leave it there tonight because we went over some other stuff earlier. So I think we've had enough problem working for the evening, okay? But the rest of the time that we have this evening is lab time, so you can work on whatever, you either, have to do yet as far as assignments, or if you wanted to be done for the night, that's okay too. I'll leave that up to you, okay? So any questions right now on the work that we did this evening? These are the start of the practice problems, okay? We will be looking at chapter 17 the next time that we're together, and then you'll be ready to kind of finish up the full assignment. If I look back at my calendar, just as a reminder, we are still on module 3 on Thursday, and I'm planning module 3 for Monday, or I'm sorry, Tuesday. These first 3 modules are on the midterm, okay? 1, 2, and 3 are on the midterm. We'll probably start 4 probably next week, okay, just to get an introduction to it, but want to make sure that you know, are all set with modules 1, 2, and 3, because that's what the midterm is going to be on, okay? So we've still got time that we're going to be spending on this that we, and then we'll also be reviewing for the midterm before we do the midterm. All right, so I'm going to stop the recording here.